Final question then, question 10, and we're asked to work out the pressure at the bottom of this beaker. We've been given the mass of the water in there, and we've also been given the cross-sectional area at the bottom. Now if we're working out pressure, we're thinking pressure is going to be force divided by area. No rearranging needed there, but we've got to be a little bit careful because we don't know the force. We're going to need to figure that one out. So the force from the water is going to be the weight of the water. It's going to be how heavy the water is. We know it's 150 grams. First of all, let's turn that into kilograms, 0.15 kilograms. But to turn it into the force, the weight of the thing, we're going to need to use the W equals mg equation. Where's my goat? Weight is mass times the strength of gravity. So this force thing is going to be the mass times the strength of gravity. Here's my mass, 0.15. I'm going to times that by the strength of gravity, which is 10. And then we're going to divide that by the area, which we're told is 3.3 times 10 to the minus 3 square meters. So you're putting those numbers into the calculator. We've got 0.15 times 10 divided by 3.3 times 10 to the minus 3. Now I know my calculator will evaluate that properly, but if I'm dividing by something at the bottom of the fraction, I often like to put these brackets in there just to make sure I'm dividing by the whole thing, just to be on the safe side. 454.54 recurring is our answer. Of course we'll want to round that, won't we? 450 pascals would be good. 454 they would accept as well. Don't forget to round your answers. 450 pascals for that one. Moving ourselves on, we have a graph. You know what? I thought I could get away without writing this down, but just for completeness, that makes me feel a lot better. Question B, we've got our two graphs here, the ocean and the atmosphere of a distant planet. Lovely. And we've been told that we need to use information from graph A to get a value for the density of the ocean water on our mysterious planet. Okay, so we're going to take data from this graph, we're going to put the equation in. It says we've got to use an equation selected from the list of equations at the end of this paper. Which equation are we going to use? Well, we know that we're given pressure, so we're looking for an equation probably with pressure in it, with depth, so some sort of value of, well, depth can have several symbols, kind of. It could be D, it could be H for height, it could be X for distance. Any of those things would be the same sort of idea. And we're looking for the density, aren't we? So those things together. Let's see. So we should have you know, that's really interesting. I've only just spotted they have assumed that it's the same gravity on the distant planet as it is on Earth, but they shouldn't have done that. So if you spotted that, well done, you're better than the exam paper. Anyway, moving on, we're looking for something like this. We know G because for some reason we're assuming it's the same as Earth gravity, like a lot of science fiction shows seem to do. So we're looking for an equation with those things in. Let's see what we've got at the back here. Wouldn't you just know it down at the bottom here? There's an equation. P equals H times rho times G. So pressure is equal to the height of the column of the liquid or fluid times the density times G. So let's get that written down. One thing you've got to be careful of, guys, by the way, is making sure that when you copy the equation from the data sheet or from the equation sheet into your calculation, that you actually do that accurately. You don't get distracted halfway through. So P is H times rho times G. Remember, this isn't a letter P, it's a curly Greek rho. Otherwise you'll get mixed up with the equation, the symbol for the actual P, the pressure there. So we've got our equation. We're trying to find density. So we need to rearrange this so that density is the subject. So I need to divide both sides by H and G, and then it was P over HG is equal to the density. So I need to have values of P, H and G. Now this graph tells me how P is affected by H. the depth of the water, the height of the column, however you want to say it. I need to pick two values basically. If I want to know a pressure and the value of H, I could go with this, 3 gigapascals and 100 kilometers. Or I could pick this one, this would be a nice one as well, 1.5 kilopascals and 50 kilometers. Either would be good. Make things easy for yourself. Pick something on the graph that goes straight through a grid line so it's really easy to read off the scale. We'll go with this one here, 1.5 gigapascals at 50 kilometers in depth. So let's put those numbers in. The pressure we said was 1.5 gigapascals. Remember, giga is times 10 to the 9, or a billion of something, divided by hg. H is 50 kilometers, so 50 times 10 to the 3, the kilometers. And we're going to times that by g, which, as we said, we're going to assume is Earth gravity of 10. In the real exam, you won't have these inconsistencies or sort of things that the examiner has overlooked. I guess they rushed this one a little bit there. Not to worry. So we put the numbers in, stick that into a calculator, and that will give you your answer. It will turn out to be, I won't stick it in the calculator here because, to be honest with you, I've got the answer right here, and there's no rounding involved. It's going to be 3,000 kilograms per cubic meter. There we are. So in terms of marks, it's 4 marks for that one. So rearranging the equation gives you 1 mark. Picking a decent point gives you another mark. So reading a pair of values off, so 3 gigapascals and 100 kilometers, or 1.5 gigapascals and 50 kilometers. Pick a point that will work for that. That will give you a mark. Putting the numbers in gives you a mark, and the evaluation gives you a mark as well to get your answer at the end there. If you've got a power of 10 error, which the mark scheme nicely describes as a pot power of 10 error, then that limits you to a maximum of 2 marks for that particular question. So if you got, for example, 3 or 30 or 3 billion or whatever, that would be a power of 10 error there. So there we are, we've calculated our density of liquid on our mysterious planet, and the final question of the entire exam. Ooh, I better not get rid of that graph too soon. Explain the similarities and differences in the pressure variation shown in graphs A and B, and your answer should refer to both the particle model or kinetic theory and to density. Well, that's nice. They've managed to structure your answer a little bit there, haven't they? They've given you some of the things that you're looking for. Obviously, to get into the 5 to 6 mark bracket, you're going to need to hit all those things. Similarities and differences between the two graphs, and you need to mention particles, and you need to mention density. So let's have a look and see what springs to mind. So if we go back to our graph, what have we got? Well, straight away I can see that this is a straight line and this isn't. We've got a curve there, so that should be worth mentioning. We've got a straight or linear relationship between depth and pressure for the water, but we've got a non-linear relationship for the pressure and height of atmosphere graph. What else can we say? So both of these are going down, but you've got to be a bit careful with this because you can see the numbers are increasing as we go down the graph here, and numbers are so they're increasing as we go down the graph here, they're increasing as we go up the graph here. So if we go deeper into the ocean, we get a bigger pressure, but if we go higher up in the atmosphere, then the pressure is actually going to decrease because there's less above you at that stage. So we've got the straight line thing, we've got the difference in terms of direction and what that's doing for our pressure there. We've talked about the linearity. Now, in terms of describing why this actually is, you know what the particles in a liquid are like. They're all kind of stuck together. They're bunched up like the balls in a ball pool. You can't really squash them into a smaller area. That's not going to work. So if you go sort of deeper down in the water, yes, you've got more water above you, but the density of the water is not really going to increase. So we're not going to find that it's a curve. Whereas when you get to the atmosphere, if you start going higher higher and higher in the atmosphere, you're actually going to find that the air density drops away. You'll hopefully be aware of this when you go up a mountain. The air is thinner, there's less air around. So if you go up high, you'll find that the pressure drops down significantly. But the big difference happens, we've got a sort of steeper part of this graph over here. So we're looking at when we've got a larger height, we've got a bigger change going on as a result of that. What else can you say? You can spot that this is in gigapascals and this is kilopascals. So clearly we've got a much larger pressure associated with water than we do with the atmosphere. And if you think about it, that makes sense because the density of water is so much greater. So if you're under 3 kilometers of water, you're going to get a lot more pressure than if you're under 3 kilometers of just air or general atmosphere. So those are the things that come to mind when you look at the graph. Let's have a look at what they've mentioned in the mark scheme in case we've missed anything. So both show increasing pressure with depth, we mentioned that. Both show a range of pressures over kilometre depths and heights. So you could talk about how both of these are in kilometres. So that's giving you a range. We've mentioned the linearity, we've mentioned the density of ocean water not changing with depth, but the density of atmosphere does. And we've mentioned the gigapascals compared with kilopascals, so the pressure is much bigger from the ocean than they are from the atmosphere. So all of those are to do with similarities and differences in the graph. In terms of the underlying physics, this is trying to explain why this is. We can talk about, not now phone, we can talk about increasing weight of the fluid because there's more molecules above. So this will work for both the liquid and the gas. It will work for both the ocean and the atmosphere. The atmosphere, as we said, becomes thinner the higher you go. These particles are more spread out. That's because gravity is pulling down the air, so most of it tends to be close to the surface of the planet, and as you go further away, the air gets thinner. There's less particles around. And there you are. So that is the explanation, just to give you an idea of the descriptors. Let's get that into frame for you. There you are. So we, of course, are going for the 5 to 6 marks. So explanation is supported throughout by linkage and application of knowledge. So we're sort of using what we already know, we're linking things together, we're using our scientific ideas of things like density and the kinetic theory, making connections logically between elements in the context of the question. And the first bullet point, which weirdly I read out, I'm reading out second, interpretation and evaluation of the information, demonstrating throughout the skills of synthesizing relevant understanding. So you're taking the stuff that you know, you're applying it to a new context, and you're coming up with ideas based on that. That is the last part of the last question. That is the end of the paper.